Limits. Limits of multivariable functions. Awesome. I've set up two here that illustrate some of the final points of these limits. Great. So we're taking a look at this first one. Over here on the left-hand side, this is as this point goes to that point from all directions, we want to find the limit of that guy. Awesome. We see that we have a domain restriction here. Sure. This domain down here can't be 0. What can't be 0? X can't be 0. And looking at the point that we're going to, it appears we're going to be continuous at this point. So because of that continuity, we can evaluate the limit directly.
I'm sure that we should do the limit of the quotient of the limits. So this is equal to the limit as x, y goes to 1, 0 of y divided by the limit as x, y goes to 1, 0 of x, and in doing that, the limit, because this is just a variable of y,
we can rewrite that. I know, I'm showing tremendous amount of detail. Some of you guys want to put the 1 there and the 0 there and get 0. You'd totally be correct. But I got all this room, so I'm going to do it formally. Because
this is a function only of y, my limit can be changed as the limit y goes to 0 of y divided by limit as x goes to 1 of x. Yeah, a little more than we need, because we still get 0 over 1. And what's that guy?
0, for sure. And then what? A box. And a flower. But wait, there's more. Something else happens up here in this limit. When we're taking this limit, we see upon direct evaluation that we have a domain restriction that says y can't be 0. What do you see there? Y is going to 0. So we got some problems. We could have a removable point of discontinuity, maybe. In that case, we'd be able to do some algebra, some manipulation until we were able to get something that we could evaluate using continuity. But why don't we show that this limit does not exist? It's not enough to just say that it does not exist. You need to show it. Awesome. So let's break this up into two parts. We're going to show on a path that the limit from the left and the limit from the right do not exist. This path is going to be the line x is equal to 1. Okay? So fix x equal to 1. Oh, great. So in the plane, this surface behaves all crazy like. Awesome. What we're going to do is we're going to look just on the path where x is equal to 1. And we're going to take a look at what happens as y approaches 0 from the left, or from the left and from the right. And we're going to see where those two
limits are. So if we fix x equal to 1, now we're looking at the limit as y from the left approaches 0 of 1 over y. Why were we able to do that? Because we fixed x to be 1. So we're looking on this path. This, as y comes from the left, is coming from negative y. So here we have 1 over negative y, which gets us, oh, really small numbers, really big. That gets us to minus infinity.
Ouch. So we see this guy is cruising straight on down, asymptotically. Now if we take a look at the limit y from the right, as that goes to 0 of 1 over y, now we're coming from positive y. And here, this is going to take off asymptotically up along the line y is equal to x, because this goes to positive infinity. And since the limit x, y from the left as it goes to 1, 0 of x, y does not equal the limit of x, y from the right, as that goes to 1, 0 of f of x, or f of x, y, which is x over y in this particular instance. Since this does not occur, then the limit as x, y goes to 1, 0 of x over y does not exist. A box. Yeah, and a bed. Let's put this one to rest.